Hello everyone, my name is Lei Zhou. I'm going to introduce my work CAFNet, Learning Temporal Camera Relocalization using Kalman filtering. As analyzed by previous investigations, accurate image-based relocalization relies on the 2D 3D matches and the projectile geometry. However, most of such works focus on one-shot methods, and no efforts are made to extend 2D 3D matching to the time domain. In this work, we will handle 2D 3D matching by learning scene coordinate regression. For temporal matching, we use Kalman filters to regularize the matching results in the time domain. Our method formulates both parts under a unified Bayesian framework. We call the framework CAFNet, which is composed of three subsystems: the measurement, process, and filtering system. It can give inference recursively. The measurement system is a generative model describing how image observations are generated from the scene coordinates. It can be denoted by the likelihood function. However, directly modeling the relationship between image observations and the scene coordinates is difficult. Therefore, we first use a fully convolutional network called SquareNet to map the image observations to scene coordinate predictions. Then we assume Gaussian measurement noise in the predictions. Finally, we define the loss based on the likelihood. The figures visualize the variances of noise. Now we come to the process system, which models the linear transition process across frames. We use optical flow warping to warp predictions from the last time step to the current step to give the prior estimations. It has three components. The first one is cost volume constructor. For each pixel, we build a cost volume from its local window. The second one is a unit-like network, which consumes the cost volume and outputs a confidence map. The optical flow is computed as the weighted average of offsets weighted by the confidences. Here we visualize the predicted flow fields over different scenes. The third component models the process noise for each pixel with three fully connected layers after the encoder. Over the occluded regions of the dynamic objects, we'll predict larger process noise. We define the loss based on the prior distribution. Finally, the filtering system fuses the likelihood estimation and the prior estimation. It involves computing the innovation and Kalman gain to obtain the posterior distribution, and the system is parameter-free. The loss of the filtering system is defined based on the posterior distribution, and the final loss of CAFNet sums up all the loss terms. To make CAFNet more practical in use, we propose to use NIS testing to detect outliers on the fly. The main idea is that the innovation is Gaussian, then the normalized innovation squared should follow the chi-square distribution. Therefore, we negate pixels outside the 95% acceptance region. We run experiments on both indoor and outdoor datasets. First, we evaluate the matching accuracy in comparison with DSAC++, which is the best scene coordinate regression method. SquareNet is a single-view version of our method. CAFNet achieves the minimum errors consistently. Here we visualize the predicted point clouds. We also evaluate the pulse accuracy of both one-shot and temporal methods. Our SquareNet achieves the minimum rotation and translation error among the one-shot methods, and the CAFNet achieves the best accuracy, except the translation error on some scenes. Here we visualize the relocalization results of image sequences. To mimic the real scenario with motion blur, we add artificial motion blur to some of the testing images and plot the cumulative distribution function of the pulse errors. We can see that CAFNet is much more robust to motion blur. Besides, we perform ablation study on uncertainty modeling. First, it leads to reasonable confusion matrix. Second, it improves accuracy of both SquareNet and OploNet. These are the visualization of the measurement noise and process noise. The brighter color means smaller noise. We have released our codes and models in this link, and thank you for listening.